circle. So this part in here, it rotate. It rotate around here. So this is R. And here is an angular speed, in which cases rotating in here at the speed omega. So we like to consider the kinetic energy involving in here. But the kinetic energy is involved is not solid, involving a bunch is with the velocity, in which case it is called v sub I. In which case we like to say this is v1. And what happened to here? This is a Ri, and then this is a Mi. You're rotating. So, so that we like to figure out they call rotational energy. We know that linear velocity, if this is a object, when you are moving with v, this is the mass is m. So if this is a situation, then the kinetic energy for this linear motion is equal to 1/2 mv squared. So this is considered as linear motion. So in the rotation motion, we cannot single out one point, in rotation motion, we cannot single out any one point anymore. They group it together. So from this point of view, we like to consider, generally, in a solid, there's a certain object point you call Mi. We really a certain point Ki, you certain or Vi squared. But we have to take the summarize on that. So suppose for total, this is an individual mass point. So now you have to consider how we do it. Okay. So then the total system, total kinetic energy, you have to summarize every single point. So kinetic energy, summarize every single point for rotation now is equal to summation I equal to 1 to n, infinite number. And then that is equal to 1/2 Mi Vi squared. So this is a rotation, it's circle. So we like to say if we circle around, so we like to take a look at one point. So suppose this is omega 1. So this is a linear velocity. So v1 is equal to r1 omega 1 omega I. Okay. Something is very important. So you have a kinetic energy equal to that. Then you have summation of I equal to 1 to the n 1/2 Mi Ri omega I squared. Because Vi is equal to Ri times omega I. So you factor this out, do this, then you have summation of I equal 1 to n, then you have bring the 1/2 on the top, outside. Then you have Mi Ri squared, then you have omega I squared. So we have to ask ourselves, during the solid motion, they're all surrounding at the point for rotation. It rotates like this, it rotates like everywhere like this. But during the rotation, with the axis right in the center, the angular velocity is identical. See? Now this is serving as explanation. That means omega 1 is equal to omega 2, equal to omega 3, equal to omega 5, equal to omega I. So because in the circular motion, respect to this axis, the angular velocity is constant. As soon as it is rotating on this axis, the angular velocity is constant. So from this point of view, we like to say omega 1 equal to omega 2 equal to omega 3, and that is equal to omega I, and then that equal to omega. So angular velocity with respect to the rotation axis, the omega angular velocity is the same. So in this case, kinetic energy is equal to 1.5 a summation of Mi Ri squared, and this is omega squared. So now you look at it by comparison. This is the kinetic energy for an object for rotation, for solid object for rotation. Now, for an object, linear motion, this is M and this is a B. For kinetic energy, for linear motion, I repeat again, for linear motion, is equal to 1.5 mv squared. Okay, now this one is a linear motion. And then the motion for linear has certain resistance. That resistance we call is we have a name for it. It's called inertia. So now we have this. This is each object point, each mass point, MI squared. This Ri is related with the moment or leverage, lever. In which cases, in order for it to rotate, it needs torque. So this, in rotation, this group of things serving as a purpose for resistance. This is a resistance to rotate. This M serving as a resistance to move. So the resistance to move we classify as inertia. The resistance to rotate, because it is related with a lever, related with moment. So we call this one is called moment or inertia. With moment or inertia, I is equal to moment or inertia. So in the kinetic energy in rotation, we will say this. In which cases equal to 1.5 I omega squared. So this is how we define the kinetic energy for rotation. So now we know something called moment or inertia. The calculation on that is I is equal to summation mi ri squared. So with this in mind, then supposedly we have a object. So I is equal to summation mi ri squared. Now we like to talk more meaningful now. Summation in a mathematical term have another meaning. It's called integration. This object right now is using circle. What happened to irregular object? So can this still apply? Yes, it still can apply. So in these cases, we like to say, if we're taking in terms of integration, this mi will become dm. This one will become r squared. So for a irregular object or regular object, we like to do this, in which cases is called r squared dm. That is the formula for calculation of moment of inertia. So different object, different shape have different moment inertia. From this, you will know, we're doing the rolling motion yesterday, you will find the sphere, in which cases has the largest speed when it's rolling down into an inclined plane. And then the cylinder has less speed. And then if you're a hollow cylinder, then even have a smaller speed. So that tells you that the shape dictates a rotation motion. Just like another people say, the person's success depends a person's characteristic. Okay, so if you have good characteristic, then most likely you will be success. Sometimes, like the president of